All right, hello and welcome back, ALEKS students. So this is an ALEKS topic that's called predicting the type of solid formed by a compound. This is a requested video, so again, thank you very much for the requests. I will be getting to them as quickly as I can. This is a newer ALEKS topic. I think it's a great topic. There's a lot of different things going on, multi-concept. You really need to understand quite a few different things in order to truly master this topic. So we're going to go through 3 different examples. I'm going to try to talk through all the different things that you might need to know. So let's go ahead and get into it. The first thing I wanted to point out, though, is that I also printed out this table. So this is a table that shows up in the ALEKS explanation page. So when you are looking at an explanation for this topic, you'll find this table. And I think that this table is a really great table. It's got a lot of information. And if you can understand everything that's on this table, you'll be in really good shape for this topic. So, maybe print it out, maybe just refer back to it every once in a while. But this is a really great starting point. And we'll go through basically examples of every single thing that we see on this table. I'll try to refer back to it, except for metals. In the examples that I pulled, I didn't get any metals, but excuse me, but we'll talk about those as well. The other thing I printed out was just the periodic table, so you'll definitely want to have a periodic table handy, and just to make sure that you know where the different atoms and elements are, and it will be really helpful for the beginning part of this exercise. So let's go ahead and get into it. The first thing that I'm going to do is basically just sort of go through this table from left to right. I'm not going to try to do everything all at once. I'm going to have a strategy. My strategy is going to be to figure out the type first, and then based off the type, figure out the force. Once I figure out the force, then I'm going to go to the melting point. That's going to be the last thing that I do. Not even going to worry about it yet. So for the type, all you're doing, the first exercise is basically figuring out of the atoms and elements that show up in your compound, what are they essentially? Are they nonmetals? Are they metals? Basically, what are they? So for HCl, I'm just going to look at, is hydrogen a metal or a nonmetal? It's a nonmetal. Is chlorine a metal or a nonmetal? It's a nonmetal. Therefore, this must be a molecular compound. And that's really it. You can maybe get confused with, well, HCl is a strong acid, so on and so forth. That's true. But all you're doing for the type is looking at this, this chemical compound and figuring out what are the species in there. Are they metals or are they nonmetals? That's it. So for barium, barium is a metal, right? So barium shows up in group 2. So here we've got barium here. It's in blue, hydrogen in yellow or orange. So since barium is a metal, and then iodine is a nonmetal, this must be ionic. So anytime you're combining a metal and a nonmetal, that means you've got an ionic compound. So we can just fill in the type based off of that. N2, this one's a little bit confusing because N2, we might look at it and say, well, voice is cracking here. My N2 is an atom, right? It's well, not atom. N2 is just an element. There's just nitrogen and nitrogen. But because we have that, because it's diatomic, because we have a covalent bond holding that nitrogen together, then this would become a molecular compound. So I think that there can be some confusion here. We'll have some examples later on that are atomic, and you might look at this and think, well, it's atomic, but it's really not because we have that N2. Because it is diatomic, then that becomes a molecular compound, and that covalent bond is very important to that determination. Okay, on to the force. Now, the force is basically going to be based off of the type of compound that you have. And we're going to need to take into account, is it a polar molecule? Is it a non-polar molecule? Is hydrogen bonding playing a role? So we're going to have to think about all of those sorts of things. So sometimes it's helpful to draw Lewis dot structures for your molecular compounds. If you are looking at HCl and you're confused that it's a polar molecule, for instance, that's something that you're really going to need to be comfortable with in order to figure out this topic. So when I look at HCl, I know that chlorine is more electronegative than hydrogen. Therefore, this chlorine is going to have a partial negative charge. This hydrogen is going to have a partial positive charge. So each one of these is going to be a polar molecule. Therefore, the force holding one HCl molecule to another HCl molecule, that's really what we're talking about. So if I've got one HCl molecule here, partial negative, partial positive, there's going to be attraction or a force holding partial positive this HCl molecule to this HCl molecule. That's what we're talking about here. The force holding the solid together. So, I could sort of draw a little This is this molecule, this is this molecule, and there's this force holding them together. This is a dipole force. So if you have a polar molecular compound, you're gonna have a dipole-dipole interaction. Ionic's pretty straightforward, it's ionic. So that one's a little bit, easy. And the thing I would be keeping in mind here is that this barium in an ionic compound is gonna have a 2+ charge, and each iodine is gonna have a 1- charge. So what we're really talking about for this barium iodide being held together is that there is a charge, an actual 2+ charge and an actual 1- charge holding that compound together. That's an ionic interaction. For this one, N2 is a non-polar molecule. So if I draw the Lewis dot structure for nitrogen, I know that that's a non-polar bond, nitrogen and nitrogen, equal electronegativity. Therefore, the only force holding this together would be a dispersion force. So if you've got a non-polar molecular compound, then you're gonna have a dispersion force. So for your molecular compounds, essentially what you're choosing between is if it's non-polar, you're gonna have dispersion. If it's polar, you're gonna have dipole-dipole. And then if it's polar and it has hydrogen bonding capabilities, if it has the potential for hydrogen bonding, then we would choose hydrogen bonding. And hydrogen bonding is really just a special case type of dipole-dipole interaction. And we'll talk about that more later on in this video. Okay, so that's how we would choose the forces. And then the melting point comes, again, from what we chose here. Now, ionic is definitely going to be the strongest. And really what we're looking at here is what are the relative charges at play here. If I've got a full 2+ charge and a full -1 charge, that's going to be quite held together, right? That's going to be a Coulomb's law type thing where positives are attracted to negatives. If I've got a full positive charge and a full negative charge, that's going to be held together more strongly than these partial positives and partial negatives. And so the melting point, essentially what we're talking about here is if you wanted to grab onto this and you wanted to pull it away from its friends, basically, so grab onto this molecule and pull it away, how strongly would you have to pull? And which one's going to be most stuck together? Well, the ionic compound is going to be the most stuck together. The dispersion, the nonpolar compound is going to be the least stuck together because there's no even partial positives and negatives. They're just very weakly held together. And then HCl is going to be in the middle. So that's the way that I would do this. Just think about what are the forces holding them together, which of these forces are stronger, which of these forces are weaker, and then base your melting point off of that. All right, let's do another example. So the next example here, we've got CH2Cl2, argon, and sodium oxide, so Na2O. Got a little scrunched in here, but Na2O, we can see it over here as well. So again, the first thing I'm gonna do is figure out the type because carbon, hydrogen, and chlorine, they're all nonmetals. Again, we could go back to our periodic table if we needed to figure out that these are all nonmetals. That means it's molecular. Here we've just got argon. So this is gonna be atomic. I've got a sort of a naked atom there. So just argon, group 8 noble gas. That's gonna be atomic. And then Na2O, so that's sodium oxide. Sodium is a metal, and oxygen is a non-metal. Therefore, this one must be ionic. And now we're going to be thinking about the forces holding them together. So for CH2Cl2, I'm actually going to draw a Lewis dot structure here real quick. So hydrogen, hydrogen, chlorine, chlorine. And this is going to be a polar molecule. So I can sort of see that from this Lewis dot structure that this end of the molecule, these are going to be partially negative. Chlorine's more electronegative than carbon. This end's going to be partially positive. So this is a polar molecule. And if I drew another one of these, CH2Cl2s, we're going to have the same sort of setup where I've got a partial positive and I've got partial negative ends. So these are going to be held together, again, by a dipole-dipole interaction. We've got a permanently polar molecule. So this is going to be a dipole force. Now, we do not have hydrogen bonding because chlorine is not that small electronegative. So hydrogen bonding is only for oxygen, fluorine, and nitrogen. On the next example, we will see that. But because this is not a hydrogen bonding interaction, this is just a dipole-dipole interaction, then that's going to be what our force holding them together is. Now, for argon, this is a case where this is going to be a dispersion force. And here's where we get into some trickiness or some confusion. So I'm going to go back to this table. Where for our atomic solid, so once we've decided that we're going to call this an atomic, type of solid, then we're going to start breaking it down here. And now we've got 3 different choices that we need to decide between. So for group 8A, so if it's a noble gas, it's going to be dispersion. So if it's helium, hydrogen, so on and so forth, not hydrogen, sorry, argon, helium or argon, or other group 8 elements, we're gonna choose atomic, and then it's gonna be dispersion force holding those together. That's because these are noble gases. They're not really forming covalent bonds with anything. They're holding on. They have a full octet. They're holding on to all of their electrons, but they're going to be held together by weak dispersion forces. If I've got a network solid, a good example of this is a diamond. So carbon. A diamond is carbon. And again, that's actually on the next example, so we'll talk more about that then. They're actually held together by covalent bonds. And this is not something that you would intuitively know. It's something that you just need to learn and then understand what that means. Those are going to be held together very, very strongly. And then a metal solid, if I've got a metal, so common examples would be iron or calcium or just other metals in the middle of the periodic table. Those are going to be held together by what we call a metal bonding force. The way in which they're held together is a little bit different. It actually gives the properties of the metal. If we think about copper, for instance, and we think about copper wire, what do we know about copper wire? It can run electricity through it. That's because of this metal bonding force, the way in which this metal solid is held together. So that's actually pretty interesting, but sort of outside the scope of what we're doing right now. But for these atomic solids, we really need to be careful about the force holding these together. Same thing with the molecular solids. We're going to have to choose between the intermolecular forces. But these are going to be sort of the trickier aspects. Ionic is easy. It's just ionic, right? And that's going to be held strongly together. But atomic solid, we need to sort of dig in a little bit deeper. And same with molecular solids, we need to dig in a little bit deeper. So argon is going to be dispersion. And then here, obviously, we've got an ionic compound, so we've got an ionic force holding them together. So now the melting point, we need to figure out, okay, which of these are more strongly held together, which are weaker. Dispersion forces are always going to be really, really weak. So we can go ahead and put a 3 there right away. Same thing with ionic, always going to be very, very strong. And then this dipole interaction is going to be somewhere in the middle. So that's going to be a melting point of 2. All right, one more example, and we'll finish this video off. Okay, so here we've got NH3, carbon, and CH4. Again, the first thing I'm going to do is I'm just going to go through this type, and then we're going to spend a little bit more time on the force, and then hopefully quickly figure out the melting point. So the type, NH3, clearly molecular, right? Nitrogen and hydrogen, both nonmetals. Carbon, clearly ionic. We've just got a single element there. And then CH4, again, with the molecular. So I actually built models of these because I had enough, of these little model kits, and it's fun to build models. So what I wanted to sort of talk about or show is really what we're talking about here when we're talking about the force, right? So this is molecular, and then what we're talking about for the force that's holding these together is if these two compounds, these two molecules are interacting with one another, they're going to be held together, right? And there's actually going to be an attraction between this hydrogen here and this nitrogen, the lone pair of electrons on this NH3. If we drew a Lewis dot structure, let's draw it like this. Then this nitrogen, right, would have a partial negative charge. That would be like this. And then this hydrogen would have a partial positive charge, and it would be attracted to that lone pair of electrons. And this fits the sort of requirements for a hydrogen bonding interaction. So going back to, what is a hydrogen bonding interaction? The way that I always like to draw a hydrogen bonding interaction is like this, where X equals O, N, or F. And this is, again, getting into a discussion of intermolecular forces. So here we've got our small electronegative element with a lone pair of electrons bonded to hydrogen, bonded to another small electronegative element. So this force is going to be hydrogen bonding. So again, you really need to be able to visualize the molecule, build a model, draw out the Lewis dot structure, figure out what that intermolecular force is. for these molecular type solids, type compounds. For atomic, this is where we have this very interesting covalent structure. So carbon is one example, and if you just look up the structure of diamond, this is actually what the structure of diamond is. It's covalently bonded carbon, where each carbon atom is bonded to 4 other carbon atoms in a structure like this. So then this would just sort of extend, right, in 3 dimensions, where every place we've got a bond here would be another carbon atom. And so the force that's holding this together, we actually call covalent bonding, because it's actually covalent bonds that are holding this carbon atom to this carbon atom to this carbon atom. And again, there's no way that you would sort of intuitively just know that. It's something that you need to learn, you need to sort of see examples of, and carbon is a good example of that. Silicon is also a good example of that. And that's gonna be held together very, very strongly. CH4, this is gonna be dispersion. So here we have a non-polar molecule, so CH4, perfectly symmetric, carbon-hydrogen bonds are non-polar bonds. So this is going to be a non-polar molecular molecule, so that's going to be dispersion forces that's holding it together. So now for the melting point, again, dispersion, anytime we see dispersion, that's going to be the weakest thing that's held together. Covalent is going to be very, very strong, just like ionic. And then hydrogen bonding is going to be somewhere in the middle. It's pretty strong, but it's not as strong as covalent, and it would not be as strong as ionic either. So hydrogen bonding, it's a strong interaction, but it's not as strong as ionic, and it's not as strong as covalent, and it's not as strong as metallic either. So a metal would be held together more strongly as well. So that's a good overview, I think. Hopefully I talked through all the different examples that you might see, but if you have any questions, feel free to leave a comment below, and thanks so much.